In the previous lecture, we have defined the notion of a linear operator, and we also defined the notion of the norm of a linear operator. So if we take two linear spaces, denote by L, E, F, the set of all bounded linear operators from E to F. If we take two linear operators, bounded linear operators, then what can we say about the sum of them? For we have that the sum of these two is a linear operator, and it is also a bounded operator by the definition of boundedness. So it is an element of this set. And if we take a linear operator and multiply it by a scalar, lambda A, then it is also a linear operator, and it is also a bounded linear operator. So it is also an element of this space, of this set, for any scalar. But this tells us that this set, LEF, is not just a set, it's a linear space. This is nice to have a linear structure of this set. The question is, can we bring some analysis to this set? So can we define metric? Can we define norm? In the previous lecture, we have defined the norm of a linear operator. Let me remind it for you. So for a bounded linear operator, which is now nothing but an element of this space, we define a norm of A is a supremum It's not difficult to check that it is in fact a norm on this linear space. So let me just conclude that if we take this linear space of bounded linear operators and equip it with this norm, then it is a normed linear space. Which is already nice, but can we get some more? We want to check whether this space is complete. Let me state the theorem. Let E and F be two normed linear spaces. And let F be complete, which means that it's a Banach space. Then the space of bounded linear operators is Banach. So we want to prove the completeness. By definition, we have to take a Cauchy sequence and prove that it is convergent in this space. That's what we need to do. So let this sequence be a Cauchy sequence, which means by definition, for every epsilon greater than 0, there exists n such that for every mn greater than n, we have that the norm of an minus an is less than epsilon. But by the definition of the norm of the operator norm, we just have that amx minus anx less than or equal to the operator norm of this difference times the norm of x in E. This one is in F. We have it for every x from E. But since the sequence an is Cauchy, this term is less than epsilon. So the norm of this difference can be made arbitrarily small, which means that the sequence anx is Cauchy. And the space F is a Banach space, which means that every Cauchy sequence converges to an element of F. In F. Say the limit anx equals to some point y which depend on x. Let us now define an operator A on E such that A of x equals to y of x, exactly this limit. Let me also say that it is nothing but the limit anx. All the operators an are linear operators. The limit is linear as well. So the operator A, which we define, is a linear operator. Let us prove that A is a bounded operator. So what we have is, we know that every Cauchy sequence is bounded. And we know that our sequence of operators an is Cauchy, such that for every n, the norm of an is bounded. Let's go with less than or equal to. Doesn't matter much. We have the norm of anx in F less than or equal to the norm of an times the norm of x, which is then less than or equal to constant times the norm of x, which holds for every n. So we can take a limit when n tends to infinity. We obtain that the norm of, and yet using the definition of the operator A, which is the limit of anx, the norm of ax in F less than or equal to constant times the norm of x in E, which means that A is a bounded operator. Well, what did we do so far? So we started with the Cauchy sequence of bounded linear operators. We managed to construct a bounded linear operator. What is left to prove that that original sequence converges to this operator? since an is Cauchy, am minus an is less than epsilon for the values am and epsilon which we specified at the beginning of the program. So let us take an element, any element from E with norm less than or equal to infinity. Then amx minus anx less than or equal to, by this inequality, then epsilon times norm x, which is less than epsilon. And now I will take m to infinity. This is the norm in F. This is the norm in F. Hence, the norm of A minus an, the norm equals to supremum of ax minus anx for every axis in E such that the norm of x less than or equal to 1 by the alternative definition of the norm. But we know that this expression is less than epsilon, which means that the norm of A minus an tends to 0 as n tends to infinity. So we started with the Cauchy sequence and proved that it converges to an element A from the space. In the proof of this theorem, we already spoken about a sequence of operators converging to another operator. And what we meant by that is this convergence of the norm of the difference. Let me write down the definition for this convergence and then discuss some more convergences. A sequence in converges to an operator A uniformly if an minus a converges in norm. So in some cases we will denote it, this converges as an 2 arrows to A. So converges uniformly. Why do we call this convergence uniform? So it's natural to call it a norm convergence or convergence in norm. Why do we use the word uniform? Uniformly, converges uniformly. As an example, if we consider the space of continuous functions with the infinity norm, then the notion of uniformly convergent functions coincide with this definition. So this definition of the uniform convergence generalizes the notion of the uniform convergence of functions. So if we consider the space of continuous functions with infinity norm. And left the sequence of functions converges to F uniformly then it's in fact if and only if Fn minus F converges in norm. Since the norm convergence, which we introduced the uniform convergence, is kind of a generalization of the uniform convergence of functions, we can think about the generalization of the other convergence of from the reality of function, the pointwise convergence. We will say that a sequence AN converges strongly to a point A. If it is in fact converges pointwise. Although this convergence is called strong, it's not stronger than the uniform. It is in fact stronger than the weak convergence, which we will consider a little bit further in this course. Since this norm is less than or equal to the operator norm times the norm of x due to this inequality, the uniform convergence implies the strong one. Exactly in the situation as in the situation of functions, where the uniform convergence of functions implies the pointwise convergence. Well, the converse is not true in the reality of functions. In the general situation of linear operators, it's not true as well. Example. Let us consider the operator P from L2 to L2. So these are the sequences summable with square. And P will be a projection on a finite dimensional space. So P of x will be xp, let me call it Pn. It will be projection on n-dimensional space. xn, x1, x2 up to xn, and then all zeros. And let us also consider the identity operator I, which is I of x equals to x. Then, for every x from L2, identity minus Pn of x norm in L2 equals to sum of the coordinates squared starting from n plus 1 to infinity and the square root. So the operator Pn keeps the first n coordinates. The operator identity minus Pn sets the first n coordinates to be 0 and keep the rest of the coordinates. So all of them are here in this sum. But we know that the sequence X is from L2. So the whole series from 0 to infinity converges. So what we have here is a tail of convergent series. When n tends to infinity, the tail of convergent series tends to 0. So, by definition, the sequence Pn converges to identity strongly. On the other hand, also for every x from L2, the norm of identity minus Pn of x in L2 is less than or equal to the norm of x in L2. So the left-hand side equals to this. On the right, we have this sum from 0, well, from 1. We're indexing the sequences from 1. Which tells us that the norm of this operator, identity minus Pn, is less than 1. I want to prove that the norm is 1. To do this, it is sufficient to find a single element, and this element will be the vector En plus 1. So all the coordinates except n plus first are zeros, and the n plus first coordinate is 1. Then the norm of identity minus Pn of En plus 1 in L2. By the way, what is Pn of En plus 1? The operator Pn keeps the first n coordinates, which are, for this sequence, are zeros. So Pn of En plus 1 is 0. So what is left here is the norm of En plus 1 in L2, which is, using the definition of the norm in L2, is nothing but 1. So the norm of identity minus Pn is 1 for any n, which means that this norm cannot tend to 0. So Pn does not converges to identity strongly. In general, the uniform convergence implies the strong convergence, but not conversely. But there are spaces on which these two convergences are equivalent. So if one of these spaces, in particular the domain, is finite dimensional, then uniform and strong convergence are equivalent to each other. So let's prove this. Let E and F be non-linear spaces. And let E be finite dimensional. Now, if we take any sequence of operators converging strongly, then it converges uniformly. Let's prove this. From the very beginning, let's use the fact that E is finite dimensional. Say the dimension of E equals to M. Then by definition of the dimension, we can find M elements of E which are linearly independent and which span E. There exist linearly independent M vectors from E such that E equals to the span of these vectors. In particular, every element from the space E can be written uniquely as a linear combination of these basis vectors. And now, using these coordinates of x, let us define a new norm on the space E. Which will be the one norm. Well, we know that this is in fact a norm, but we also know that in finite dimensional space, any two norms are equivalent. Then, in particular, this one norm and the original norm on E are equivalent, which means that there exists a constant M such that the new norm is less than or equal to M times the old norm. I will denote it as norm in E. Now let us take X with the norm less than 1. Less than or equal to 1, and consider an of x minus a of x. Using the fact that X can be written as a linear combination of the basis vectors, and the operators A and AN are linear, we can write it like this. Now I will use the triangle inequality to write it like this. And now, instead of every norm like this, I will take the maximum of all of them. And by taking maximum, I can factor this out, and what is left is the one norm of X. Well, we have just said that the new norm and the old norm are equivalent. So this norm can be estimated by M times the old norm, but yeah, I forgot to write here that the norm of X, the old norm of X, is less than 1. So subscript E over here. So I can estimate this norm by M times the old norm, which is less than 1. So just by M. Hence, AN minus A, the operator norm, by definition is the supremum of AN minus A of X over all x's with the norm, old norm, less than or equal to 1. Okay, this is what we have by the definition of the operator norm. But we have just estimated this norm by this expression. But we know that the sequence AN converges to A strongly, which means pointwise. So for any point X from the space, in particular for every EK, it tends to 0. As n tends to infinity, which means that, well, I already wrote it, which means that AN converges to A strongly. The next result will be about an operator which is defined on a subset or subspace of a linear space, and this subspace is dense in the whole space. And it will tell us that by continuity it is possible to extend an operator from a subspace to the whole space. So let E be a non-linear space and F be a Banach space. Let E1 in E be a dense subspace. If an operator defined on E1 to F with values in F is a bounded linear, then there exists bounded linear operator A tilde from E to F such that A tilde of X equals to A of X for every X from E1. So on a subspace they do coincide. So it is in fact an extension. And moreover, the norm of the operator A tilde equals to the norm of the operator A. Well, the idea is to define this operator A tilde outside of E1. So it is defined on E1 because we want it to be coincide with the operator A. So we want to define it outside E1. And this is where we will use the density. So let X be an arbitrary point from E. So since E1 is dense, so the closure of E1 is E, then there exists a sequence Xn from E1 such that this sequence converges to X. Let us now, instead of this sequence Xn in E1, consider the sequence A Xn in F. Using the definition of the norm of the operator A, we have since the sequence X converges, it is Cauchy. So this estimate tells us that the sequence AXN is Cauchy. And since the space F is a Banach space, this sequence converges. Let's call the limit of this sequence y of x, since it depends on x. And this is an element of f. Let us first of all show that this limit is unique. So let us take another sequence xn prime such that it converges to x as well. And let us denote by A this limit, and by B the limit of the sequence A xn prime. We have norm of A minus B using the triangle inequality can be estimated by it is clear that the first and the last term tend to 0 by the definition of the limit. This term tends to 0 as well, and I will explain why. So we have this estimate, and over here we have the norm of the difference of two sequences, which tends to the same element, so it tends to 0. So we have proved that this limit is well defined, and using this limit we will define a linear operator on the whole space E. This operator is well defined, and also by linearity of A and the linearity of limit, it is easy to verify that it is linear. Let us check that this operator is in fact an extension of the operator A and that they non-coincide. So first, for every point x from E0 from the subspace, we can consider a constant sequence by definition of the operator A tilde we have so the operator A tilde is in fact an extension of the operator A. Let us now check that their norms coincide. Having this estimate, we can take a limit as n tends to infinity. And we will get this holds for any x from E. And so the norm of A tilde is less than or equal to the norm of A. Let us prove the converse inequality. By definition, the norm of A tilde equals to supremum over all x's from E such that the norm of x is 1. Now, instead of taking the supremum over the whole E, I will take the supremum over the subspace E1. But now x is from the subspace E1, and we know that A tilde and A coincide on E1. So it equals to AX but this is nothing but the norm of A. So the norm of A tilde equals to the norm of A, and we're done.